In this video tutorial, we'll explore support vector machines, which is a powerful supervised machine learning algorithm that is used for classification or regression tasks. Right, so here we have an example of a data set that consists of two classes, which can be clearly separated by a line. Okay, so these data sets here, they are portrayed in 2D. Okay, so the question is which is the best line that can be used to separate these two data sets. So this is where the support vector machines come in. So support vector machines work by finding the optimal decision boundary, okay, here, which is called a hyperplane. So this hyperplane best separates the different classes. Okay, so let's start by understanding this linearly separable case of the support vector machines. So here in this figure in the left side, it's showing the case that we can separate these two classes. Okay. So the optimal hyperplane here, this dashed line, separate these two classes. So here we have the green, say representing the forest, and then the brown representing non-forest. And then the two solid lines here define the maximum margin, which is the widest possible separation between the two classes, as you can see. Okay, so the data points closest to the margin, these data points closest to the margin that are marked in red are called the support vectors. So these data points, they are critical in defining the decision boundary. Okay, so the decision boundary is shown by this equation, right? So this is just the normal vector and the bias, right? So what is important here is that these points, they are critical in guiding this optimal hyperplane, which is very important. So say for example, if a point falls to this side, then it's going to be classified as say forest. If it falls to the other side, then it's going to be classified as non-forest. So here we don't have any problem. Right, so let's look at the case in the right side where we have some misclassification. So in this case, we have this just a large margin, the maximum margin. And let's say we have some misclassification that, for example, we have a point here, which is non-forest, or a point here, which is a forest in an area which is non-forest. So this represents the cases in the real world where we don't have clearly separable data points, because here some of these points violate the margin. That is, they fall in the wrong side of the margin. So how does the support vector machine work in this case? So the support vector machine will still find an optimal hyperplane, but allows a soft margin, meaning that some of the points can be on the wrong side of the margin, so that we can improve generalization. So this is critical for the support vector machine. So when we are using support vector machine, we need to fine-tune hyperparameters to achieve the best model performance Okay, so the hyperparameters control how the support vector machines make decisions, so affecting the margin size, the decision boundaries, and its flexibility. Okay, so we talk about some of the most important hyperparameters for the support vector machines. Okay, so we have the regularization parameter, which is called C. So this regularization parameter controls the trade-off between maximizing the margin and allowing the misclassification. Okay, so if we have a high regularization parameter, that means that the margin is tight. Then we have a few misclassification. But the problem is that we have a risk of overfitting. For example, if we introduce a new point. Okay, so this is a case. For example, here we have a low C. Okay, when we have a low C, that when we have the lower regularization parameter, then we are going to have a wider margin, and then this is going to allow more misclassification. But then the risk is underfitting, which is also problematic. Okay, so here I've just shown you these figures so that you can try to understand that choosing the right regularization parameter, the C, is very important. And this depends on the dataset and your flexibility. So you can see very clearly here that here, in this case, we have the C equals 1, and this is how the decision boundary appears. So when C equals 100, the decision boundary appears as this. Right. Another important regularization parameter is gamma. Okay. So this gamma governs or controls how much influence a training sample has on the classification. Okay, so this is also very important. And then if we have say a low gamma, then we have a more generalized decision boundary. Okay, so that is influenced by faraway points. Right, so this means also we have a risk of underfitting. And then if we have a high gamma, we have a more localized, decision boundary. So here, if we've got a high gamma, then it means that there is a risk of overfitting, because there's influence from the nearest neighbor. Right, so what is important to take into account is that for the support vector machines, we have these two important hyperparameters, and the regularization parameter C determines how strict or flexible the decision boundary is. Okay, and then gamma affects how much a single data point impacts the classification. So balancing between the regularization parameter C and gamma is crucial to avoid underfitting or overfitting. We will look at this at some point later. Right. Now let's just jump into a simple exercise, as we have done with the k-nearest neighbor. We are also going to use the same static data sets that we have used before, which shows the forest and non-forest classes. And the first thing is here we'll create the data set Here I've just used a data set of 400 points with 3 features, that is green, red, and near-infrared bands. And our target is the 2 classes, forest and non-forest. And this is just how our data set looks like for the 400 points. Right, next we are also going to create a function in order to plot a decision boundary, as we have done with the k nearest neighbor. So this is just a simple function for plotting the decision boundary. Okay, so let's look at the first example of a linear support vector machine. Right, here we are going to call in the sklen class, the SVC class, which contains the support vector machine algorithm for classification. Right, so for the first case, for the first linear case, we are going to define these parameters. Okay, we have the regularization parameter 10, and random start is just so that we have reproducibility. We keep it, we can run the code again and then we get the same result. And then we have, for the case 2, the regularization parameter, which is 100. And then if we run this code, we are going to produce this decision boundary. So you can see for the regularization parameter of 10, we almost have this decision boundary. And for the case of the regularization parameter C, which is 100, this is our decision boundary as well. But what we can conclude here is that the support vector machine, which is linear, is not doing a good job at classifying the forest and non-forest. Okay, so what do we do? So if we have a case of data which is not non-linear, what can we do? So in this case, we need to use what we call the kernels. Okay. So kernels are very important because we have seen that here we cannot use a straight line. Okay, we can use the linear, this line to separate the 2 data points. So we need to adopt another approach. So in this case, we need to use a curved decision boundary in order to separate these 2 classes. Okay, so here we use what we call the kernel. Okay, so this kernel trick is very important because it allows the support vector machines to transform these data sets into a higher dimensional feature space. Okay, and so what are the kernels? Okay, so kernels are just mathematical techniques, okay, that transform the original data set into higher dimensional space. So if we transform the data set, then it will be possible to separate the 2 classes. All right, so we have different types of kernels. So the most common one used for the support vector machines are the polynomial. Okay, so we have a polynomial as the first one. So the polynomial is quite good because it just captures the interactions between features by raising them to a power. Okay, so this is it's just mapping the input space to a higher degree polynomial feature space. Right, so we are just raising to a power is shown in this equation. So this is good for data with curved patterns. So Let's run here an example to illustrate the polynomial kernel. Right here we are just defining the degree, okay, to be 3, and then we have our regularization parameter 10 and 100. So if we run, this is what we get. Again, there is a slight change in the separation of the data set. Okay, we can still see that there's not much change, okay, in trying to separate these two data sets. So another kernel that we can use is called the Radial Basis Function kernel. Okay, so this just measures similarity based on distance from a central point. Okay, you're just using this to measure distance. Okay, similarity based on distance from a central point. So this is commonly used, especially in remote sensing. So many studies have used the radial basis function to do that. Right. If we plot again using the regularization parameter of 10 and 100, this is what we get. So as you can see, there's a change here in the decision boundaries. For the regularization parameter of 10, we see a slight change compared to the polynomial. And then for the regularization parameter of 100, we see that there's a more concerted effort to separate the two classes. Right, then finally, we have the sigmoid kernel. So sigmoid kernel is similar to a neural network activation function. And this is useful when data is not structured in a simple pattern. Okay, so in remote sensing image classification, we have few examples of use of this kernel. But again, here if we run with a regularization parameter of 100 and of 10 and 100, this is the result that we get. Again, not quite useful, but again, this is just a depiction of these different kernels. Okay, so this is the different types of nonlinear support vector machines kernels. Right, so let's look at some of the strengths and limitations of support vector machines in general. So support vector machines are effective in a high dimensional space. They are quite good because they introduce kernel functions for nonlinear classification. And then they also have the robust margin, which can also handle some outliers in case that data is outliers. And it is less prone to the local minima than the neural networks. When we look at neural networks for deep learning, we are going to talk about the local minima. And then limitation is that you have to tune the hyperparameters, as we have seen. You need to find an appropriate regularization parameter, the gamma, and choose the appropriate kernel parameter. So this can be time consuming. And the support vector machine is quite difficult to interpret when we compare to other methods such as decision trees. And they can be very computationally expensive, especially if you run them on large data sets. And again, this is also sensitive to scaling, as we have seen with the k-nearest neighbor. Right, so this is just a quick introduction on the support vector machine. We'll be using or testing some of these parameters when we run on actual real-world datasets for the classification of land use or land cover examples that we'll look at later. So thank you very much for watching this video. See you in the next.